So I'm going to talk a little bit about transition metal dichalcogenides, a little bit about MBE, and a little bit about STM. So it's sort of a mixed talk. How many people do MBE here? 2, 3, 4. So a small fraction of you. Okay. So, well, all right. Let's just get going. So this is just a plot of the different phases you can get in different kinds of quantum materials. So here you have spin-orbit coupling, and here you have Coulomb interaction. Okay, you might have seen graphs like this. This is just pictorial. But basically, you know that when you have low spin-orbit coupling and very little Coulomb interactions, you get simple metals. If you crank up Coulomb interactions, of course, you get interesting phases like high temperature superconductivity. However, recently we've been interested in materials which have strong spin-orbit coupling. If you restrict yourselves to areas where the Coulomb interactions are very small, and you crank up spin-orbit coupling, then you get the topological band insulators, which are very easy to calculate using a lot of our conventional numerical techniques. And however, I guess the most difficult systems to actually tackle in terms of calculations would be materials where you have both strong spin-orbit coupling and strong Coulomb interactions. In any case, in each of these quadrants, as you might say, you get very interesting phases. As it turns out, transition metal dichalcogenides are right in the middle. And so this is one of the reasons that makes them so attractive. They have moderate Coulomb interactions and moderate spin-orbit coupling. And because they have both of these to some extent, you can get a huge variety of interesting phases. So TMDCs in general, you can get spin-orbit coupling, which is moderate and therefore can give you stuff like quantum spin Hall effect, like in tungsten ditelluride. You can get moderate but important correlation effects. One example would be tantalum disulfide, which is actually supposed to be a Mott insulator. The nice thing is because these are moderate, you can actually model these theoretically. The nice thing also is that many of these materials are layered 2D materials, and because of their 2D nature, you can cleave them repeatedly and make devices on monolayers and bilayers. They're also amenable to thin film growth. So that's very nice. And finally, the band structure of these materials, amazingly, can be tuned in a variety of ways, right? Not only by doping, which is our conventional way, but also by changing the thickness and by strain. These compounds have been known for a very long time. There are many, many of them. And you have, corresponding to the fact that you have all of these nice interactions like spin-orbit and correlation effects, you have a wide spectrum of physical properties. You can get insulators, semiconductors, semi-metals, as well as metals. The other thing you have in these systems is you have a wide variety of crystallographic types, which are polymorphs. These things crystallize in multiple structures, and I'll talk a little bit more about these structures. Very popular ones are the 2H configuration and the 1T configuration. Okay, so let me just show you, for example, here. So we're talking about dichalcogenides, right? So the X can be tellurium, selenium, sulfur, and so on. And M is a transition metal, like tungsten, niobium, and so on. So here, for example, in the 2H configuration, these green balls are the transition metals, and the little yellow dots are the chalcogenides. And the difference between this 2H stacking and the 1T stacking is actually in the position of these chalcogenides. So you can see here in the 2H, they're right on top of each other. And in the 1T, the two chalcogenides are not right on top of each other. Okay? So just to give you a few examples of the different kinds of materials you can get, if you have molybdenum and tungsten and your chalcogenide is a selenium or a sulfur, then it's likely to be a semiconductor. notice what it says here, the band gap decreases with as the atomic number is increased. So as you go from sulfur to selenium to tellurium, by the time you get to tellurium, actually, you might end up in a semi-metal. For titanium and tantalum, as your transition metal, if you have sulfur or selenium, you get a very interesting compounds. These are often charge density wave systems. Both tantalum disulfide and titanium diselenide are extremely interesting CDW systems. And the other thing about these systems is that they can be made superconducting by many, many different ways. You can dope them and make them superconducting. Titanium, you intercalate with copper, it becomes superconducting. Tantalum, you add iron, it becomes superconducting. You can also pressurize them to make them superconducting. You can gate these to make them superconducting. If you have molybdenum or tungsten and you have tellurium, then these are often semi-metals. And in fact, both of these compounds, molybdenum ditelluride and tungsten ditelluride, are actually wild semi-metals. The interesting thing here is that you can also make these materials superconducting, but the superconductivity is expected to be exotic. So people talk about perhaps getting something called a wild superconductor, or at the least, the superconducting autoparameter is expected to be exotic. So there's a 2012 review in nanotechnology which gives you a short list of compounds. But since then, actually, this list has grown much bigger. You can see already in here, if you start with niobium, you can get, it can be a metal, it can be a superconductor, it can have CDW, depending upon what the chalcogen is. Same with tantalum, molybdenum, and tungsten. So all of these, niobium diselenide, you know, is a superconductor. Tantalum disulfide is a superconductor. It also has a CDW. This is a mod insulator. Molybdenum ditelluride is a wild semimetal. Tungsten ditelluride, it is really interesting. It's a wild system if you add something to it, but it also in the monolayer form, it has topological properties and is superconducting. So let me just briefly talk about polymorphs, because I'm going to show you some STM topography, and you can actually tell the difference between a couple of different polymorphs of these. So here's a 2H compound. So this is the side view and this is the top view. If you're looking at STM, mainly what you see is the chalcogen atoms. So you'll see the selenium or the tellurium. If you look carefully, you can see that they're all arranged in a hexagonal fashion. So at least between the 2H and the 1T, by looking at STM topography, you can't tell the difference between the two, okay? However, the 1T prime is different. You can see that these, for example, if these are selenium, they're arranged in an up-down fashion. And because of that, in STM topography, you'll see stripes for the 1T prime systems. The interesting thing is each polymorph actually has a different property. Often the 2H versions are insulating and the 1T prime versions are metallic, although this is not always true. For example, you know, niobium diselenide, which is often found in the 2H polymorph, is a metal. It has multiple bands crossing the Fermi energy, so the chalcogen also matters. So here are some STM examples. MOT2 is a wild semi-metal. It crystallizes in the 1T prime phase if you play with it nicely. And you can see in STM it has these stripes which correspond to these up-down arrangements. The vanadium diselenide, this is a thin film, actually, or a bulk crystal in the 1T phase, and it has a charge density wave. So you can see hexagonal arrangement of atoms. Superimposed on that is a CDW. Niobium diselenide is 2H, and if you could remove the CDW from these two, they would look identical, actually. So, but the thing is, and niobium diselenide also has a CDW, and that's what you're seeing here. Okay, So that's just a brief overview of why transition metal dichalcogenides are so interesting. So I'm going to talk about MBE, and the question is, if these things can be grown beautifully in single crystal form, you can get nice big single crystals. So why bother to go into thin films? And actually there are many, many reasons. One big reason is, surprisingly, when you go from the bulk to the thin film form, especially in the monolayer or bilayer limit, you can have properties that are completely different from the bulk. So this is what I'm telling you here. Let me just show you. This is, so Fe, Sc, Fe, Te, tin telluride, these are not transition metal dichalcogenides. I just put them here just as examples to show you how materials can be very different in their thin film form. But let me just start with these. So I think a lot of you know this. Iron selenide is a very interesting superconductor. However, if you grow it as a monolayer, its Tc can go up by a factor of 10. Right? You can go from 8 Kelvin to 80 Kelvin simply by growing FeSe on STO. This is really interesting. FeTe is an antiferromagnetic or spin density wave system, and it's actually not a superconductor in bulk. However, people have shown that if you grow FeTe on top of bismuth telluride, it develops a gap. And so it develops a particle hole symmetric gap, which almost looks like it's becoming superconducting. So this system is extremely interesting because you have a few interesting things. You have magnetism, superconductivity, and topology all in one place. Tin telluride, which is grown on bilayer graphene, was shown to be a room temperature ferroelectric, whereas the bulk is not. Niobium diselenide, which I'll actually talk about today, in monolayer form is something known as an Ising superconductor. So niobium diselenide, as far as we know, is a conventional superconductor. However, if you grow it in monolayer form, the spin-orbit coupling becomes very important. And in an Ising superconductor, what happens is the kind of spin-orbit coupling you have makes the spins point in a direction perpendicular to the plane. And because of that, you have this very special superconductor where superconductivity can exist up to very high in plane magnetic fields. By high, I'm talking about 30 Tesla or 40 Tesla. Titanium diselenide is an interesting CDW. Some people think it's an excitonic CDW. And shockingly, both in niobium diselenide and in titanium diselenide, the CDW survives all the way to the monolayer. And in niobium diselenide, as I said before, so does superconductivity all the way to the monolayer. Tin diselenide is interesting, especially grown on graphite, because there's been one work showing that it has a particle hole symmetric gap. And the question is this material actually superconducting? The gap size is pretty big, so if it were to be found to be superconducting, it would be a pretty high temperature superconductor. Vanadium diselenide, again, in mono or bilayer form, was shown to be ferromagnetic, while the bulk is not. This is still controversial, and so we're working on many of these systems. For example, we've grown all of these thin films. In fact, we've grown all of those thin films that are on those lists. That's on that list. Okay, so one beautiful thing about transition metal dichalcogenides, which I'm very excited about, is the fact that they can be tuned, their properties can be tuned by gating. And this has, so normally if you just use dielectrics to gate, you can't really change the carrier concentration by much, maybe 10 to the 12, 10 to the 13. This is in 2 dimensions. And this is a bit of a problem because, normally bulk carrier concentrations can be much higher than that. However, transition metal dichalcogenides, in a few layer limit, if your Fermi energy is maybe close to the bottom of the band or inside the gap, then even if you were able to tune the carriers by this number, you might actually be able to push the Fermi energy, a little bit into the conduction band or valence band and maybe get superconductivity and so on. So this can be really exciting. In fact, this has been done in both titanium diselenide, also in tantalum disulfide and tungsten ditelluride. People have been able to backgate and get superconductivity. Of course, for transport, another thing you can do is use gels to gate from the top, which we can't do with STM. If you use that, you can increase your carrier concentration quite a bit, up to 10 to the 14. Okay, so that was the short, a very brief summary of why transition metal dichalcogenides are interesting. You know, there are many, many different reasons. Now I want to move on to talking very briefly about MBE. So MBE, as you know, is a powerful tool to grow thin films. So we have actually 2 MBE systems in our lab, and you can see from the way they look, they're both home built. Now you might have seen commercial gigantic oxide MBE systems. The nice thing about chalcogenide MBEs is that they don't have to look like that. They can be small vacuum chambers hiding under this aluminum foil, and the walls don't have to be water cooled. You can basically build your own MBE in about $250,000. And most of that money, so a large fraction of the money goes into the reed, which is about $35,000, $40,000, and then most of the rest of it actually goes into purchasing the evaporators. So you know, an MBE doesn't have to cost $1 million. So what are the main components of an MBE system? You need a vacuum chamber, which you can't see very well here. I'm sorry about that. You need a reed, a system. This is a reed I'll show you in a few minutes. Reed is really, really critical because it actually allows you to see the film as it's growing. You need a quartz crystal monitor to know how much material you're evaporating, as a rate of evaporation per second or per minute. In our case, we have something called a vacuum suitcase. So we take our MBE grown films directly from our MBE systems to the STM without breaking vacuum using this vacuum suitcase. And you need a load lock to get your samples in there. And that's it. It's as simple as that. Our evaporators are at the bottom underneath the table. So this is actually a photograph of our evaporators. You can see they're sticking out like this, 1, 2, 3. We can put 7 evaporators, and you can sometimes double up these evaporators. So we can have about 10 elements in our MBE system. So it's a tiny system. It's not very big, as you can see here. Okay, so what do you use? Just like in crystal growth, you have various control knobs for MBE. Then one thing about MBE that you do have to think about a lot is the choice of your substrate, which can be many, many things. Sapphire, which is alumina, is very, very popular. Silicon 111, gallium arsenide, graphene, graphite, strontium titanate. This is just a small list of possible substrates people use. Substrate preparation is really important because you're thinking about growing a few layers. Your substrate must be clean. There are many ways to clean substrates. One nice thing you can do is simply anneal to high temperatures, which works really well for some substrates. Before that, of course, when it's outside, you sonicate an isopropyl, an acetone, and so on. But eventually, when you put it inside your UHV chamber, annealing for some substrates seems to be enough. You can also sputter clean. You can oxygen etch and so on, and you know it gets progressively more painful depending upon the substrate. But in our case, for many of these cases, we can simply anneal and get away with it. The temperatures do you have to? So it depends. So for example, STO, you have to anneal pretty high, 1,000 degrees. Alumina, yeah, I can't remember exactly what my students do, but maybe 600, 700 degrees, yeah. And the third important thing is the growth temperature. The nice thing about chalcogenides is that they grow at pretty low temperatures. So you can grow many things at around 300 degrees. FeSe, which is not dichalcogenides, I just mentioned this because a lot of people are interested in this. It actually is grown at a much higher temperature. So vanadium diselenide, for example, is one of the highest temperature materials. We've actually grown it at 450 degrees. And we found that depending upon the growth temperature, you can get different phases. You can either go into the 1T phase or the 1T prime phase or the 2H phase. And after you grow, you anneal. And typically you anneal at a temperature that's slightly lower than the growth temperature. Sometimes you skip this step, but most often you anneal. The growth rate is really important. We grow really slowly, but sometimes if you grow too slow, then the film will not grow, so you have to sort of play around with this. And finally, the flux ratio. Like Judy was saying, sometimes you have to really bombard the material with the chalcogen. So for example, when we grow selenides or tellurides, we put in 1:30 or 1:10 the amount of the stoichiometric number that you need. That's because of the way, these things have high vapor pressure. So if you don't, saturate the atmosphere with selenium, it'll actually basically evaporate from the surface as the film is growing. Okay, so one of the things we use when we grow films in an MBE system is reed. I'm not a reed expert, I have to confess. My students know reed really well. So I'll just give you a very superficial overview of how reed works, and I'll just give you some examples. So the way reed works is you have an electron gun. And it's this angle here is very, very small. It's a few degrees. The electrons hit the sample, get diffracted by the crystalline surface, and are detected using some kind of a detector. It's a CCD or something else. Depending upon what you have, your reed can look very different. And in fact, just looking at the reed experts can tell you, is this a good film? Is this a bad film? Is it growing in an island fashion? Is it growing layer by layer? For example, if you have 3D islands, then your reed should look like spots. If you have layer by layer growth, often you have streaky kind of reed patterns. So let me tell you what we do. A lot of the materials that we've been growing recently have been grown on bilayer graphene. And what we do is we take silicon carbide and we flash anneal it many, many times at high temperatures to make graphene on top. So this is the reed pattern for silicon carbide. You can see the dots. Those dots tell you that it's a 3D crystal. Once you've flashed annealed it enough number of times, you get graphene, and you know you have graphene because suddenly you see these lines, and they tell you that you've grown graphene on the surface. Okay, and then you can take this graphene on silicon carbide, and we use that as our substrate to, for example, grow vanadium diselenide. And now let's say this is not a full layer of vanadium diselenide, it's 0.75 of one layer. So you can see the original graphene streaks are here in pink, and then you get these new streaks, and that's the vanadium diselenide. And depending upon the angle of the substrate, you can see different things. So this is the 110, 1110, this is the 1120, this is rotated by about 30 degrees. But you still see that once you flash anneal, you get the graphene streaks, grow vanadium diselenide, and here in this case, it's a one monolayer, the graphene's almost gone, and you can see the vanadium diselenide streaks. Okay, so here are some examples of different reed patterns on for different films. Vanadium diselenide, titanium diselenide, niobium diselenide, and these are two different polymorphs. one thing I want to point out is that their lattice constants are very, very close, 0.33, 0.35, 0.34. So simply by looking at the read pattern of something, it's really hard to tell. You better be evaporating the right compound because, you can't tell by looking at the read pattern. However, you can see all of these streaks. One interesting thing is going from 1T to 1T prime. I don't know if you remember, in 1T prime, you have the chalcogens going up and down and up and down. That doubles your, in one direction, doubles your, it doubles your real space periodicity. So in Fourier space, you get these extra streaks at half the periodicity. So at least you can tell the difference between 1T and 1T prime. Okay? So look at this. We've been able to grow both 1T and 1T prime vanadium diselenide, and we did this simply by changing the growth temperature. Okay, so here's what our substrates look like. This is actually one of our substrates. This is bilayer graphene. You can see the bright and dark spots. That's the moire pattern that you expect from bilayer graphene. This is, for example, 2H niobium diselenide. This is a pretty large scan. And you can see it grows really well, right? This is probably 2 layers. Maybe one of these very light ones might be a single layer. These are the sort of the monolayer films we've grown recently. We've grown monolayer and bilayer niobium diselenide, vanadium diselenide, titanium diselenide, and in each of these cases, there's a particular reason. Niobium diselenide, because superconductivity in the monolayer limit is very interesting. Vanadium diselenide, because it's expected to be ferromagnetic, so we were hoping that if the ferromagnetism is strong, we might be able to use it as a substrate to grow a topological insulator and get proximity effect. So that's the reason to grow this. And in fact, while playing around with it, we found we could grow both of these polymorphs depending upon the temperature. The nice thing about vanadium diselenide, which might also be a problem for magnetism, is the fact that even in the monolayer and bilayer limit, it has this really nice CDW pattern. It's CDW. You can see it as a pattern superimposed on the hexagonal arrangement of atoms.
Does the lattice constant change much for the monolayers?
No, it doesn't, and I'll come to that in a second. So one nice thing about growing on graphene is I don't know the actual reason for this. The films that we grow on graphene are sort of very decoupled from the substrate. So they're almost like they're floating on top. And I'll tell you why we know this. First, we don't see any strong moire patterns in any of these films, right? And secondly, I'll show you, in fact, for niobium diselenide, I'll show you a spectra taken on the bare graphene substrate and the niobium diselenide. And the graphene doesn't seem to influence the density of state in the niobium diselenide at all. So yeah, I think maybe they just sort of, many people have noticed this.
Have you done like cross-sectional imaging to see if there's like a sulfur atoms maybe before you actually grow your layer?
No, but we know the height. The height matches what we expect. So these are all monolayers, and here's titanium diselenide. It's shocking actually that the CDW survives. In all of these, it's really surprising that the CDW survives. Yes? Yeah, they're taken at different bias voltages. Yeah. So now we come to STM, and what I'm going to do is I'm going to sort of try to give you a feel for what we can measure using STM, and I'm going to march you through a few case studies. How much time do I have?
20.
Okay, fine. So I have 4 case studies, and we'll get as far as we get, okay? Just to give you a flavor for what STM can do above and beyond giving you nice, pretty pictures. So many of you probably know how an STM works. I'll just mention it briefly. So you have a very sharp needle, metallic needle that you bring to close proximity of a surface without touching. So this is about a few angstroms. And you apply a small potential difference between what we call the tip and the sample, and electrons can tunnel quantum mechanically from the surface to the tip or vice versa. And the thing that we measure in STM is the tunnel current. And that's the only thing we measure. What we can control is the bias voltage. In fact, zero bias voltage is the Fermi energy. That's when the Fermi energy of the tip and the sample line up. And then anything we do with the bias voltage moves the Fermi energy of one with respect to the other. I'll show you that in a second. We can also control temperature. We can control the height between the tip and the sample, right? We do that using piezoelectrics. We can turn on a magnetic field. We can make the tip magnetic. And I think that's it for the moment. You might think of doing exotic things in the future, like turning on light and seeing what happens. But that, there's not a lot done in that direction yet. Most STMs that we use, in fact all of them, are used at low temperatures. This is really important to us because low temperature allows us to get high energy resolution. It also allows us to have clean surfaces for large periods of time, for months at a time, for example. So we can sometimes make measurements on the same sample for 2 or 3 months. So we have 4 STMs, and one thing I want to point out is this commercial system. The nice thing about this was actually funded by the Moore Foundation. The nice thing about this system is that when we grow our films, we can put it into this tabletop STM, quickly look at the film and take it out all within one day. So it really gives us the ability to screen our samples very fast. So the beauty of STM, right, is that you can make all kinds of different measurements and get information both in real space and in momentum space. So today I want to give you a flavor for how you can get momentum space information from STM using 2 things. One is QPI, and the other is Landau level spectroscopy. Let's see if I can get to that. So how does the STM work? When you bring the tip and the sample in close proximity, the Fermi levels instantaneously line up, okay? Because electrons flow from one to the other by tunneling and they line up. Now when you apply a bias voltage, let's say you raise the Fermi energy of the sample with respect to the tip, for example. And you can see what will happen. The electrons from the filled states of the sample will tunnel into the empty states of the tip. So your tunnel current is naturally, you can see this actually right here, is proportional to the integrated density of states from EF to this point, right, of the sample, as well as the integrated density of states of the tip. So what we try to do is we want to make sure that the tip doesn't affect our measurements too much. So we try to find tips where the density of states is pretty constant. So we try to take the tip out of the picture by doing that. So the tunnel current I, like I said, is proportional to the integrated density of states. So this delta function is just counting the states. How many states do you have from 0, which is the Fermi energy, to the bias voltage, which is somewhere here. So that's the number of states you have. That's the delta function counting. But then notice one really important thing. In STM, because of the way STM works, you need to have the wave functions actually overlap between the tip and the sample. And because of that, the tunnel current is proportional to the square of the wave function as well. So each state is weighted by the square of the wave function. So in the z direction, what this means is that the tunnel current is exponentially sensitive to the distance between the sample and the tip. And that exponential sensitivity is what gives us atomic resolution. So then we can get images that look like this. You guys are probably very familiar with these kinds of images. This is BISCO. This is gold 111. You can see monoatomic steps, right? One layer of atoms and step and another layer of atoms. Gold 111 has a herringbone reconstruction on the surface. That's what these zigzag patterns are. And you can also see it has a two-dimensional electron gas on the surface. You can see these lines parallel to the step edges. That's the 2-deg bouncing off of the step edge and interfering, causing an interference pattern. So you can see all this with an STM. But then you can, because the STM, the current is proportional to the density of states, integrated density of states, the differential conductance, di dV, is actually proportional to the density of states at any given energy, okay? So what we can do is measure this differential conductance either by measuring I versus V and then taking and differentiating that, or much better than that, we use a lock-in technique to directly measure di dV as a function of the bias voltage. So for example, if you would put your tip at one point and measure di dV, for a normal metal, here's Fermi energy, this is zero bias, you would simply get a flat straight line across the Fermi energy, so metal is pretty boring. Whereas in a superconductor, you would see no density of states at the Fermi energy, and then you would see these coherence peaks on either side. So that's what STM spectra look like. But like I said, the tunnel current is proportional to not only the number of states, but is weighted by the square of the wave function. And because of this, we have information on wave functions in STM. And from this, we can get momentum space information. So let me give you, let me just quickly run through what quasi-particle interference is. When should I stop?
10 to 15 minutes.
10 to 15 minutes, okay. So the technique is actually quite simple to understand. You have, let's say you have electrons on the surface of your material, and here your electron is a wave, of course. So here's the scattering center, it's coming in, and then it gets scattered by the scattering center to some other direction. The incoming and the outgoing waves interfere with one another, and you get an interference pattern right where these overlap, right? And you can understand this, the periodicity of this interference very easily in one dimension. So let's say you have a one-dimensional free electron gas, and the electrons have this very simple wave function. So if you were to just measure normal 1D electrons, psi squared is a constant because, you know, it's e to the ikx. You square that, you get a constant. You don't see anything. But let's say you have a scattering center. You have an incoming wave and a backscattered wave. This is e to the minus ikx. And now when you square the wave function, you get this kind of a cosine term, and that gives you waves. So in general, if you have scattering, then the psi squared is proportional to cosine of the incoming, the outgoing minus the incoming momentum. Okay? So this is how you measure, you get information on momentum using STM. So this is just an example. Copper has a surface state which has a parabolic dispersion. The electrons on the surface of copper literally behave like free electrons, except with some kind of renormalized mass. Okay, so here you see a di-dv map, and you have many scattering centers. And here's what it should look like in momentum space. And now, if this works, hang on for 1 second. It's trying to connect to the internet, sorry. If you take a Fourier transform of this image, you get this circle which represents all the scattering vectors in this image, okay? And you can do this as a function of energy. And let's say we start from the bottom of the band where, you know, the circle is small, and we go to higher energies. You will see an ever-expanding circle, and that's your dispersion. So you get this circle that increases as a function of energy. This is above the Fermi energy. And you can plot this and you can plot the radius of the circle and you get the dispersion, energy versus momentum. And for the surface states on copper, you get parabolic dispersion. Okay, so QPI is very, very powerful. You can get momentum space information. The other thing about quasi-particle interference is these Fourier transforms reflect the topology of the Fermi surface. So in this case, the Fermi surface was circular, so the Fourier transform looks circular. In bismuth telluride, for example, where the Fermi surface looks like a hexagon, our Fourier transforms also look like hexagons. So we can get really a huge amount of information using these techniques. So the first case study I want to do is how we can use QPI to probe electron-phonon interactions. The reason I put this first is this is something you might not have seen before. You might have seen, you can use QPI to get band structure. That's very common. But the fact that you can actually get quantitative information on electron-phonon interactions, this you may not have seen. So how do you do this? So remember what electron-phonon interactions give you. So here's just like a parabolic band, right? This is in 2 dimensions. Here's the Fermi level. If you turn on electron-phonon interactions, this is just Ashcroft and Merman. What you expect to see is the dispersion as you go across the Fermi level develops a small kink, right? That's it. That's all the effect of the electron-phonon interaction is, if it's not very strong. If it's very strong, you'll get a charge density wave or a superconductor or something, right? So you can use this kink. So our goal when we started doing this was to actually measure this kink and to use it to get a measure of how strongly the electrons are coupled to the phonons. And that's actually given by something called the Eliashberg function, which is alpha squared times F. F is just the phonon density of state spectrum as a function of omega. And alpha is how strongly each phonon couples to the electrons. Okay, so this alpha squared F encodes all of that information. So we wanted to measure electron-phonon coupling using the STM. So what did we really want to do? So here's the surface of copper. Here's the dispersion. Here's the Fermi energy, 0. We wanted to look very close here and see if we can see a kink in the dispersion. Okay? So that's what we were trying to do. So what do we do once we see a kink? Right? First, let me just go back to some very basic thing, which is what are we measuring? We are measuring the imaginary part of the Green's function, which is the density of states. And if you have electron-phonon coupling or any interactions of any kind, all of the interactions effects can be encoded in something called the self-energy. So the imaginary part of the Green's function looks like this. This EK is just the bare dispersion, right? This is the real part of the self-energy. This is the imaginary part of the self-energy. So what this is telling you is that the imaginary part of the self-energy broadens things. So if you have interactions, things get broader. The real part of the self-energy shifts things. So if you had a band at some momentum K and energy E, the real part of the self-energy shifts it around a little bit. Okay? So the question is, oh, wait, is everything looking like it's Greek? Sorry about that. So how do you get the self-energy due to electron-phonon coupling, right? This self-energy. You get it from alpha squared F. But measuring alpha squared F is not simple. So what we wanted to do was to measure alpha squared F by measuring the self-energy. That was our goal. Okay? So let me just, in the next few minutes, I might not be able to get very far, so let me just finish this part, which is I want to give you a model calculation. It's really a very simple calculation for what you should expect for copper. And then I want to measure the dispersion near the Fermi energy for copper. I want to see the kink and see how the calculation compares with our measurement. Okay? So forget about all this text. All I want to tell you is that if you knew alpha squared F, you can get the self-energy, which means that if you can measure self-energy, you can invert this to get alpha squared F. So the self energy and alpha squared f, the Eli-Ashberg function, are intimately connected to each other mathematically. Okay, and there are many ways to get one from the other. So our goal is to do the following. First, we're going to do a simple calculation assuming an alpha squared f, calculate the self energy, and then get the dispersion, and you can see what that looks like. And then I'm going to measure the real part of the self energy using STM, and then you can compare the two and see how they compare with one another. So here's a model alpha squared f. This was actually done using a calculation in 2002 for copper, right? So this is what your phonon density of states looks like, and this is what we used as an input. And by just using this alpha squared f as an input, we got the real part of the self energy and the imaginary part of the self energy. That's what they look like. And now we can calculate the dispersion. Everything looks the same except something has changed near the Fermi energy. And there you go. You can get this slight kink. This is the calculated dispersion specifically for copper, because we know the band structure of copper really, really well. Okay, so can we measure this small kink? Here's our data. And if you have a lover's eye, you can sort of see a kink, but you don't have to do that. We can take line cuts at each energy, and we can figure out the peak positions, and this is our dispersion. And now I hope you can see the kink in the dispersion, which is this is 0. And so this is a particle hole symmetric feature that you expect for electron-phonon interactions. And now what do we do with this information? Remember what I told you, we're measuring the imaginary part of the Green's function, well, the Fourier transform of that, but in any case. So the real part of the self energy simply shifts the bare dispersion. So in order to get the real part of the self energy, if we knew the bare dispersion, we could subtract the actual measured data from the dispersion to get the self energy. And so this is extrapolated from high energies. This is the bare dispersion extrapolated from high energies. You subtract the two, and there you go. This is the real part of the self energy. Okay? And now we can compare the calculated self energy with the measured self energy. And you can ask the question, how well did we do? Let me just try to answer it in a few different ways. The first thing, the magnitude of the change. This is 2 MeV, by the way. That is very, very close. So this tells you that at least we got the approximate strength of the coupling between the electrons and the phonons right. However, look, the calculated self energy has all of these little wiggles, and our experimental self energy is missing all these little wiggles. As it turns out, if we had actually wanted to use our experimental data and invert it to get alpha squared f, without the little wiggles, you will not get an actual alpha squared f. So the answer is we did pretty well on some, on some scale. But however, in order to get all these wiggles, we have to work harder and do more precise measurements. So we actually used Landau level spectroscopy, and we did another work. You can read this paper if you're interested. And we actually measured the self energy very precisely with all of the little wiggles, and we inverted it to get the Eli-Ashberg function. We did this for a topological crystalline insulator. Okay. So I don't know if I have time. Do I have 2 minutes, or am I? Okay, 2 minutes. Okay, so let me just in the next 2 minutes show you just a couple of slides on monolayer niobium diselenide. So we were very interested in niobium diselenide because it remains superconducting to the monolayer at the monolayer limit. We grew 2 layers of graphene, bilayer graphene on silicon carbide, and then we grew either 1 or 2 or 3 layers of niobium diselenide. And we measured the material spectroscopically using STM. So this is what it looks like on very large length scales. And if you zoom in, most places you can actually see the CDW. So if you look this triangular arrangement of atoms, this periodic arrangement, that's actually this charge density wave in niobium diselenide. Now, and here's the thing. Now, if you look here, you can see areas of graphene. Those are the dark areas, right? Like that's graphene. So if you go to graphene and measure the density of states, it looks like this, right? Which is sort of expected for graphene. It's sort of V-shaped. However, if you go on niobium diselenide and you measure the density of states, it looks like this. It's completely different. So basically, this tells you that the niobium diselenide is pretty seriously decoupled from the graphene underneath. Interestingly, niobium diselenide in the bulk is a metal, but this looks like a semiconductor. And as it turns out, when you thin the material down to the monolayer limit, a lot of the bands are pushed away from the Fermi energy, and there's only one band that actually crosses the Fermi energy. And that's another reason we were interested in this system, because it turns into a one-band superconductor, which we might be able to tune into different regimes simply using gating. This, if you zoom in right here, close to the Fermi, you can actually see the little kink right here. You see this gap? This is the charge density wave gap of niobium diselenide. It's about 5 millivolts, okay, or something like that, between 5 and 7 millivolts. Okay. Now, if you zoom in some more, look at this energy scale. It's much smaller. You can see the superconducting gap. It becomes a better and better superconductor as you go from the monolayer to the bilayer to the trilayer. But certainly, even in the monolayer limit, you get a nice superconducting gap with coherence peaks. So this is for the bilayer. If you change temperature, you can watch the superconducting gap go away as a function of temperature. So it disappears around 3 Kelvin. So it's a 3 Kelvin superconductor, which is pretty high considering it's just a couple of layers. One thing to notice, though, is this line shape. So here's what a BCS superconductor would look like in red. So, and the black is our measurement. So it doesn't look quite like a BCS superconductor in this limit. The interesting observation that we made is the following. We turned on a magnetic field, and what we found is the following. So look at this. We're marching through different fields, 0, 1, 2, 3 Tesla, and so on. You go from 0 to 1 Tesla, the bottom of the gap lifts up, the coherence peaks are suppressed, that makes sense. You get to 2 Tesla, same thing, the bottom lifts up some more, the coherence peaks are suppressed some more. But beyond 2 Tesla, 4, 6, 11 Tesla, there's no change. Essentially, you end up with a pseudo gap. And the magnitude of the pseudo gap is very, very similar to the magnitude of the superconducting gap. Now, in bulk niobium diselenide, by now the superconducting gap should have disappeared. Certainly by 6 Tesla, the gap should have disappeared. So the question is what's going on? And we see this effect, the pseudo gap effect, even at high temperatures. It's perpendicular, yeah. So this is not icing. So the in-plane field definitely, it's an icing superconductor, but this is for a perpendicular magnetic field. So what could this be? One thing people have known in the past is that if you can separate these 2 energy scales, which is the pairing energy scale, which sets the gap size, from the phase coherence or superfluid energy scale, which sets TC, then you can have a separation, then you can have a situation where you get a pseudo gap. And this happens, for example, if you introduce disorder. So the simple question to ask is our sample disordered? And how much disorder do we have? And I'm going to actually quickly flash a couple of slides and I'll be done because I think I'm running out of time. One thing you can do to quantify disorder is to ask, do we see quasi-particle interference? Because if you don't have quasi-particles, you won't see quasi-particle interference. If your quasi-particles are broad, you won't see quasi-particle interference. So this is another thing I wanted to tell you. QPI is a very good probe to ask the simple question, how good are your quasi-particles? And so in the case of niobium diselenide, we see clear quasi-particle interference. these rings, right? You can see the dispersion. The size of the ring gets bigger. And you can actually compare our dispersion in red with green, which is the data taken from ARPES. So in any case, we have good quasi-particles. I'm going to actually stop here. So basically, we have a mystery. We have a pseudogap in the system. We don't have a huge amount of disorder. We have a little bit of disorder. We know that because the coherence peaks aren't very large, and the bottom is a little lifted, even at 300 millikelvin. So what is the pseudogap? What is the role of dimensionality? And what does this high field phase actually look like? What are we actually seeing? Is this a sort of a interesting soup? Maybe you have pairs, but you don't have phase coherence. But how do these pairs survive up to 11 Tesla? Yeah, so, okay, I'm going to stop here.